Another one of our Thursday meetings. Good afternoon again, everybody. And again, welcome to one of our Wednesday afternoon meetings. We're carrying on with the theme of what to do with our variables and our statistics today, with Professor Heft talking to us again about anticipating statistics. So this is all very important in the planning of your project. So without spending too much time dithering, Richard, I'm going to hand over to you directly.
Right, thank you for that, Colleen, and welcome everybody. In terms of preparing your data for statistics, it is something that I've discussed fairly recently. So I've decided to change the topic slightly and talk about something that many people have been asking for, and that's sample size and how to predict and calculate sample size. So I've taken this from the most recent course on statistics that I presented. I think it should be possible to understand it, even if you haven't done the course in statistics, but I certainly would recommend that those who haven't attend one of my courses on biostatistics. We'll certainly do another one in the second semester of this year. So let's go straight to a PowerPoint presentation then. Right, so this particular talk is titled Calculating Sample Size. First, I want to use a very useful analogy. Most of you will probably remember this, and if not, it shouldn't be too difficult to remind you of something that you would have learned in your first year physics, and in fact, almost certainly at school if you did physical science. And that's Ohm's law of electricity, which tells you that in any electric circuit, the voltage is equal to the current times the resistance. I want to show you practical examples of this because it's a very, very useful analogy for the things that we have to take into consideration when we understand the principle of sample size and how to calculate it. Right, so voltage equals current times resistance. The current is the amount of electricity flowing through this wire. The voltage determines on the battery that you put in there. You're well aware that many batteries are 1.5 volts, but we also get 6-volt batteries and 12-volt batteries, etc. And then the resistance is not only the wire itself, but also useful things placed in the circuit, such as this light bulb. This light bulb has resistance. The effect is that when the electricity goes through that resistance, heat is given off. And it's that heat that turns a wire white hot to give the actual light that comes out of the light bulb. So if we know any two of these three, we can calculate the third, such as this. Let's say, for example, that I tell you the resistance of this light is 2 ohms. That's the unit of resistance. And the current flowing is 6 amps. You all know what that means. What is the voltage? Easy. Voltage equals I times R, so it must be 12 volts. So if we knew the current and the resistance, we could predict the voltage. Now, what about if I double the batteries here so that we now have 24 volts worth of batteries? The same light, what current is flowing? Simple rearrangement. If V equals I times R, I must equal V over R, which is going to be 24 volts over 2 ohms, so it must be 12 amps. As simple as that. And again, this time we knew a different 2 members out of the 3, but it still allowed us to calculate the third. And the final example, if I tell you that the current flowing is 3 amps and the voltage is 24 volts, my question is, how many light bulbs have I got there? Well, rearranging that, R equals V over I. 24 volts over 3 amps is 8, and seeing each lamp bulb was 2 ohms, there must be 4 light bulbs. So working with Ohm's law is actually very simple. Now, this is why I call it our direct analogy. For practical purposes, calculating anything to do with power and sample size requires us to understand that there are once again 3 components. 2 of them everybody's heard of: the power of the study, the sample size, but the effect size seems to be greatly overlooked and ignored and not well understood. Yet it's every bit as important to this relationship as were voltage, current, and resistance. Without understanding all 3 of those, we couldn't have done any of those calculations. And similarly here, if we don't understand power and sample size and effect size, then we can't understand this relationship. But conversely, once we do, provided we have any 2 of those 3, then we can calculate the third, as we've just been seeing with the electricity experiment. Right. So this enables us to calculate the sample size we need for a study. It's going to be more or less the power of the study divided by the effect size. So therefore, again, effect size becomes a critical component. Similarly, effect size is proportional to power of the study over sample size. And power of the study is proportional to sample size times effect size. So given any 2 of those, we can predict what the third will be. Now let's start with power. Okay. I'm getting an unstable internet connection. Just let me know if I go offline. Right. Here's the definition of study power. Power is the probability that a test of significance will pick up an effect that is present. In other words, that a test of significance, one example being student's t-test, will pick up an effect. In other words, will return a result of p less than or equal to 0.05. That's what we mean by picking up an effect, that it's present. I'm going to show you in a minute that it's quite possible to have an effect present, but be unable to show that it's significant using statistical tests. In that case, we have a low power, an underpowered study. On the other hand, if just about every time the statistical test comes out positive, significant, then our study obviously has a high power. It's adequately powered. So that is the effect there. To paraphrase that definition, power is the probability that a test of significance will detect a deviation from the null hypothesis. Again, p will be less than 0.05, should such a deviation exist. The fact we need a definition like that immediately tells you once again that it's possible for a test of significance not to detect a deviation, not to be significant, even when such a deviation actually does exist. And it's almost always because the study was inadequately powered, which almost always means the sample size was not big enough. Right. So just because a real effect is present does not mean that you'll necessarily be able to show significance. That is the problem. It's quite possible for any of us to conduct a study and not show significance. And yet when somebody else comes and conducts the same study, but with a larger sample size, they suddenly are indeed able to show significance. So their study must have been better powered than our study. Right. But let's now turn to this quantity of effect size that nobody seems to understand. It's very simple. Firstly, let's distinguish between effect size and significance. A highly significant difference does not necessarily imply that there is a, if we're using, for example, a difference in means, that there's a large difference in means. It doesn't mean that it has any practical implications. Okay? All it implies is that there's a very low probability of such a difference having arisen through sampling error. So a highly significant result does not mean a huge difference or a very important effect practically. I have had students who've turned up P less than 0.001 who said, wow, look how big the difference is. That's not true. Okay? Statistical significance does not necessarily mean a large effect or any practical significance. Right. And I think it's worth just taking a pause there and looking at an Excel spreadsheet and seeing exactly what we mean. Right. So here's a simulator that I've made. Okay. And over here, I can actually, just got to get zoom out the way, I can set some figures. I'm going to say that I give 100 Rand pocket money a month to the boys, but there's a bit of a spread, so I'm making a standard deviation of 12, which means that some get 75 Rand, some get 125 Rand, but most get round about 100 Rand, okay? And then I'm going to be very prejudiced, and I'm going to give the girls 99 Rand, right? Now I can actually set the population on this spreadsheet, which is over here. Okay, I've called it treated and controlled. Think of it as boys and girls. So here are a whole lot of boys. Here are a whole lot of girls. These are the allowances I give them every month. And I have deliberately set it so there is a real difference. Okay, if we just look slightly over, I've just got to get zoom out the way again. In actual fact, there's a double check here, maybe too small. The boys have come out as 99.7 and the girls at 99.2. Okay, so one is getting 50 cents more than the other out of 100 Rand. Okay, I'm now going to take samples out of that large population and see what means I pick up for my samples of the two groups and the difference between them, which we know is half a Rand or 50 cents. So let's take a sample size of 20 from each group. Okay, the values I picked up was 97.7 for boys, 100 for girls, in fact, the wrong way around. And the t-test P was 0.495. If I did it repeatedly and repeatedly, P equals 0.813. P equals 0.375. I'm not showing significance. Let me now take a sample size of 500 from each group. Here I got a difference of 1 Rand, okay? Still not showing significance, so it's getting better. And in fact, on one occasion, I managed to show significance. 5 times I didn't, once I did. Now we know there is a real difference. So this is in fact a study power of about 20%. I've got a 20% chance of showing significance. 80% of the time, I'll miss it. Let's do a few more. Okay, there again. Occasionally, I am able to pick up that significance. It needed a much larger sample size of 500, but I'm still not picking it up reliably. So let's take a sample size of 1,000. Okay, and we do it again. Not significant, not significant. I'm starting to pick it up again, not very reliably. So even a sample size of 1,000 is not really doing it. Okay, what I'm going to do now is make the difference just a little bit wider. So I'm going to say 98 for the girls. Okay. Yes, and in fact, the difference between the two groups really is 2. So the point I'm making once again is that there really is a difference between the two groups. The question is, will our study pick it up? Let's go back to a sample size of 500. Significant, significant, significant. All the reds are less than 0.05. Significant, significant, oh, not quite significant, significant. What we've really achieved here is 80% power. 80% of the time we are picking up a significant value. 20% of the time we're missing it. If we set this on 1,000, we've actually now got, well, not quite 100% power, but almost. We are very reliably picking up significance. If we go to a sample size of 200, we're picking up significance about half the time. In other words, our power is now about 50%. If we go to a sample size of 100, most of the time we are not picking up significance. There, occasionally we do. That's probably what, a power of about 5% or something, maybe, less than 10%. Less than 10% of the time we are showing the significance. So this study is now underpowered. For that size difference of 2 Rand, a sample size of 100 was not enough. A sample size of 200 seems to give us a higher power, not perfect. A sample size of 500, very much more satisfactory, and is giving us a very much higher pickup rate, statistical significance. It all depends on which sample is chosen out of that population. So on 200 and 100, it was underpowered. On 500, it appears to be adequately powered. But what I want to show, at least one, oh, look at these, 0.007, 0.000, 0.007, 0.001, those are highly significant. And yet the difference is 2 Rand out of 100. Okay, even enough to buy chewing gum these days. So for all practical differences, whether you get 100 Rand or 98 Rand a month makes just about no difference at all. You can't buy anything, sad these days, with either 98 Rand or 100 Rand. So the fact that it's highly significant does not mean a very, it just means that there is a very high ability that they really are different, that the boys and girls really aren't getting the same amount of money. Right, so we'll go back now, but we've made a couple of points. Firstly, that highly significant does not mean a major difference or a very important difference. And secondly, we've shown how changing sample size dramatically affects your ability to show significance, and how frequently you would show significance if you did the sampling repeatedly, right? And that, we said, is your power. The higher the power, the greater the chance that your test will be significant when you do it. The lower the power, the lower that your chance will be test significant when you do it, even though a real difference does indeed exist. So in other words, you'd be with a low power study you tend to miss significance, even though there really is indeed a real difference. With a much better, adequately powered study, you tend to pick up significance when it's there. So that just makes that point. Let's go back to PowerPoint. Right. Now, what influenced significance? Those of you who've been on my course will recognize this. Those who won't, haven't, may not, but don't panic. It's not necessary to understand it. All I want to say is that the higher your Z score is, or your T score, or anything else, the more significant your result is. Right. So what is going to make this value Z bigger when our study is comparing two means, as in, is systolic blood pressure higher in women than in men? Do rats fed a particular substance live longer than another group of rats that didn't get that substance? That sort of common experimental design. Well, what will make Z bigger? A bigger difference in means obviously is going to make Z bigger. If this is 10 minus 2, leaving 8, we'll have 8 on top. If it's 3 minus 2, we're going to have 1 on top, which is going to be much smaller. So the bigger the difference in means, the more likely we are to show significance. And that is effect size. What is the size of the effect of that substance you fed the rats? Does it mean one group lived 8 months and the other group lived 1 month? Or does it mean one group lived 8 months and the other group lived 7 months? The first one is a very much bigger effect size than the second. Right. But that's not the only thing that determines how big Z is. Down here, we've got standard deviations. Okay. And if you don't get confused by all of this, what you'll see is that the smaller the standard deviations, the larger the total denominator will be. And if you divide a numerator by a bigger denominator, you're going to get a smaller number. So Z will become larger. For example, 8 divided by 2 is 4, but 8 divided by 16 is only 0.5. So the smaller this total number down here, the better for significance. And that we can do by making a smaller standard deviation, which means that your data points are less spread out around the mean. But now there's a third way we can determine what Z is going to be. These are the sample sizes of the two groups, N1, 2. And if you look at the maths of it, the bigger N1 and N2 are, the higher Z is actually going to be. Okay, the higher Z is, the more easily you're going to show significance. So bigger sample sizes make it easier to get statistical significance. Whenever Z is over 1.96, P is equivalent to 0.05 or less. Right. So this tells us that a big effect size, a big difference in means, smaller spread around the means of your sample, and larger sample sizes all increase your chance of getting significance. In other words, all increase the power of your study. So there's effect size. Right. So effect size is just how different, for example, are two groups. 100 Rand as opposed to 50 Rand is a big effect size. 100 Rand versus 98 Rand is a small effect size. 100 Rand versus 99 Rand 80 is a tiny effect size. But if your sample size is big enough, you can still show P less than 0.001 for any of those. So significance does not tell us necessarily how big the effect size is. Right, so practically, what is effect size? Now, perhaps I won't go into too much detail on this, but if you do understand correlation, for example, height on the y-axis, mass on the x-axis, okay, degree of education on the x-axis, income on the y-axis. Those would both be correlations, as Colleen said last week. Okay, then the figure we calculate, Pearson's R equals, is in itself a measure of effect size. The higher R is, the more we know that the X value is influencing the Y value. And for practical results, R equals 0.1 is a small effect size and 0.5 is a large effect size. I'm actually going to just skip through this one. Those who haven't been on the course will probably find this bit confusing. Right. But for difference in means, we need other measures of effect size. Right. So, two samples here. There's the difference between mean 1 and mean 2. It's 100. Okay. There's a difference between 600 and 1,000. That's 400. Now, you might think that the second one is a bigger effect size, but in fact, it's not that easy. It depends, as we said, on the spread of your results as well. Each of those is a sample, and you can see that the values you measured are clustered very tightly around the means. Those are narrow curves. That means a small spread, which equates to a small standard deviation. And the gap between them obviously looks wide. On the other hand, here's a samples where the standard deviations, the spread, are very wide indeed. And you can see that even though the gap here is 4 times bigger, it really doesn't look nearly as impressive. In the first case, with the second mean, just about every member of the sample is completely different to the first sample. Here, only a few members are completely different to the first sample. Okay? Most of the members of the second sample are in fact no higher than at least some members of the first sample. So the effect size actually is not nearly as big as we think here. It hasn't had the same effect on the individual data points. On the other hand, if we shrank the sample deviations, the spread like that, then that again would become a very big effect size. Just about every member is completely different to every member of the first group. So effect size is not the same as the size of the difference. You have to take account the standard deviation as well. So 2 factors determine effect size. The magnitude of the difference, which is mean 2 minus mean 1, but also the spread of each sample, okay, which is known as the variance, or its square root known as the standard deviation. Right. So here's a practical example. Now, just remembered I haven't put this right. It's slightly the wrong way around, but it doesn't matter. You'll still pick up the point. Let's assume you're an Olympic swimmer, okay? And in the heats, it turns out that the mean finishing time for this particular race was 150 seconds. The standard deviation was 10. That means some people did it in 100 and, oh, I already have got this wrong, okay. This would, yes, this should be about 130, because 2 standard deviations below the mean would be 130. 2 standard deviations above the mean would be 170. So I've in fact got my numbers wrong there. But the point is there's a wide spread. Okay, right. Let's compare that with a situation where everybody was very much closer. If the standard deviation were 1 second, that means just about everybody finished between 148 seconds and 152 seconds, as opposed to 130 seconds and 170 seconds up top. That would be the meaning of the smaller standard deviation. Right, if we put them on the same scale, you can see exactly what I mean. This group with a narrow standard deviation, everybody finishes much more tightly bunched up than the group at the top with a higher standard deviation. Now let's assume you are there, bang in the middle. So in the heat, you finish exactly halfway through on the median. Half are below you, half are above you. But now the next step is, in the finals, you improve your time by about 3 seconds. I apologize, this is the mistake I meant. It should, of course, gone to the left to give a shorter time. I've shown it going to the right, but the principle is still the same. A change in 3 seconds. Now, that's all very nice, but it hasn't really made a major difference. It just means that instead of coming 10th, you came 6th or 7th. And sadly, there are no medals for coming 6th or 7th. You were still soundly beaten by 5 other people. But let's say the situation were here, the narrow standard deviation, and you improved your time by 3 seconds. That would take you out to the front and you would get a gold medal. So I think that's a good practical demonstration of why the practical effect of a size is very dependent on the spread of the sample. Okay, if it's widely spread, then an improvement doesn't change your relative position much. If it's narrowly spread at the bottom, then the same improvement has a major difference in putting you ahead of everybody else. So it's a practical example, okay, of how standard deviation is as important as the actual difference in the means in determining effect size. Now, a common measure of effect size is called Cohen's d, and that's just defined as the difference in means over the standard deviation. That's an average of this of the two curves. Right. So for example, here, Cohen's d effect size is 3. Why? Because the difference in means is 3. The standard deviation is 1. 3 minus 1 is 3. So here, Cohen's d is 3. That's a measure of effect size that takes into account both the difference, the size of the difference, and the spread of results expressed in standard deviations. Right. So in this case, all right, your difference of 3, this time I've shown it the right way around, is 3 over a standard deviation of 10, which is 0.3. So your Cohen's would be about 0.3. Okay. Sorry, I've calculated 0.7 there. On the second setting, the standard deviation is 1. Your difference is 3. Okay. So your D is in actual fact 2.6 because it wasn't quite 3. All right. So there's a very big Cohen's D at the bottom and a much smaller Cohen's D at the top. So again, the Cohen's D has taken effect of both the sample size and the standard deviation. And it's shown that in the second situation, the effect is actually much more important, larger than it is in the first case. So these are practical examples of Cohen's D. A small effect, 0.2, means there's a huge amount of overlap between the two curves. As D gets 0.5, so the difference becomes more and more marked relative to the standard deviations. There's 0.8, it's already regarded as a large effect. only 53% overlap of the two curves. And here's a big, very big effect. D equals 2 is only 19% overlap of the two curves, but there is still overlap. By the time you get to about D equals 5 or something, there'll probably be just about no overlap at all. Right. So there's D, difference in means over the standard deviations. There's a similar thing called hedges, but that's for different shaped curves where you pool, you weight the average as opposed to just a straightforward average. So now that we understand power, effect size, and sample size, we can go back to how we started and see how we start balancing these three. Using that relationship, the power is proportional to the sample size times the effect size. So,
Richard, can I just disturb you one moment? I'm sorry.
Sure.
On the Cohen's D, your denominator is the standard deviation. Is that the standard deviation for both distributions, or both distributions have the same standard deviation?
Yes. So it's the average of the two distributions. If they're the same, then it'll just be one distribution because it'll be the same for both.
Sure.
That's
Okay.
the average. That
So you'll add the two standard deviations and divide by 2.
Different standard deviations. Sorry, got that?
Yeah, thank you. Thank you.
Good. Right. So what could result in the power of our study improving, which would be a good thing? Okay. We could increase sample size. That's straight maths. Okay. And we could increase the effect size. So if we have a larger sample size, we'll have a larger power of the study, a greater chance of finding significance. And similarly, if there is a bigger effect size, then we've got a greater chance of finding significance. Both of those will increase power. Okay. So going the wrong direction. What if we want to find a smaller effect size? Let's say, for example, we've got a suspicion that the difference in our rat survival is not going to be 8 months versus 2 months, 6 months, which might be a big effect size. It's going to be 8 months versus 7 months, which is only 1 month. For the same standard deviations, that will be a much smaller effect size. Well, how can we be sure that we can compensate for a small effect size? Okay, using exactly the same reasoning, we're either going to have to accept that the power of our study will go down. In other words, we are less likely to show significance. Okay. Or we can increase the sample size. Now, obviously, we don't want to decrease the power of the study. So what we will do is increase the sample size. Then it'll become possible for us to determine significance with a much greater probability, in other words, a higher power, for a smaller effect size that we wish to measure. In the same way as we saw that we couldn't pick up a difference of 2 rand with a study sample of 200 in each group, that's effectively n equals 400. But we could do it when we had 500 in each group, effectively a sample size of 1,000. So to detect a smaller effect size, you have to have a larger sample size. Or you must accept that the power of your study is going to go down, less likely to show significance. Right. Obviously, that's not what we want. Now, what about sample size? Okay. What happens if I decrease sample size? If you look at the maths of that, that either means that the power of the study goes down. In other words, I'm less likely to find significance, or it has to mean that I must accept that I can only detect a bigger effect size. So if you reduce sample size, you have the consequence that you'll only be able to measure very big effect sizes, not small effect sizes. So if the difference in your rats is 8 months versus 2 months, you'll probably get away with a very small sample. If the difference in your rats is 8 months versus 7 months, you're going to need a very much larger sample. So you see now how sample size and power and effect size are all related. And you can't calculate anything without knowing at least 2 of those 3. So this concept of effect size is as important as power and sample size. So how then do we estimate sample size? Right. Okay. Well, this is a sad thing in life. Those who've been to see the statistician will know. Statisticians don't understand the phrase, don't answer a question with another question, because that's what they always do. Okay. So you go along and say to the statistician, what sample size do I need? And they never just give you an answer. They ask you questions. Okay, well, what power do you want? Fortunately, by convention, we usually just accept power of 80%. That means that there will be an 80% chance we will show significance if indeed there's a real difference. Okay, so the statistician doesn't have to ask you too much about that. But his next question is, what effect size are you expecting? Okay. The answer to which is almost always, what's he talking about? Okay. So then the statistician explains to you that you need to tell him what your result is going to be. How big is the difference going to be? And what will the standard deviations be of your samples when you measure them? In other words, he wants to know what's the difference in means and what is the pooled standard deviation. And the reason you're totally thrown is you haven't yet even done the study. No, you're still at the point of putting together the protocol and the ethics application. And in effect, what the statistician is asking you to do is to tell him what your result is going to be. And that, I think, is probably the main reason why people get so absolutely flawed in the sense of FLOORED when they go to see the statistician. He or she is asking them to tell him or her in advance what result they're going to get. But as you've seen now, you can't calculate sample size unless you're able to give a suggestion of what the effect size will be. So the statistician is asking you which of those is going to apply. A little difference with small standard deviations, or a big difference with small standard deviations, or a little difference with big standard deviations. Sorry, the middle one should have been big difference with big standard deviations. The first one and the second one are quite likely to show significance fairly easily with small sample sizes. The last one is going to require very large sample size in order to show significance. And that's why the statistician can't help you unless you're able to, look into the future and take a sensible guess at what difference you're going to find. Right. So if we actually approach this in order, to be absolutely correct, in order to calculate sample size, the first thing we need to know is what level of significance are we required to show. And that's easy because in biomedical science, we've all agreed by convention, P equals 0.05 is what we want. So that's really not a problem. The second thing is we have to decide on the power we want for our study. That's the probability of actually finding significance if it exists. Okay, we won't worry about the definitions of beta error now. We usually select a power of 0.8. Okay, in other words, an 80% chance that our statistical test will come up significant if there really is a difference. Below that power, there's just too much chance that we'll get a non-significant result, even though our experiment really has worked and there really is a difference. But now we also have to make that informed guess at the effect size we think we will find. Now, depending on the type of test, we may have to predict means and standard deviations or a correlation coefficient, whatever sort of statistical test we're doing. I've used the example here of means and differences. So how are you going to do that? You haven't done the study. Well, you have to use intelligent prediction guesswork. Here are some examples: existing knowledge. Well, somebody else has done a very similar experiment. They found that the difference between the two groups of rats was 4 months, and they found that the standard deviation was 1 month for both groups. So now we can plug that in for effect size. Or there may be analogy. Okay, look, I don't know what's going to happen to these rats, but I do know that there's another toxin which is quite similar to this one. And when that was used, rat survival was halved. So I'm going to assume it's about the same. It's going to be eight months versus 4 months. Or you may do a pilot study and just say, well, I've tried it out in 10 rats. Okay, 5 lived for 8 months and the other 5 lived for 4 months. So I think it's reasonable to assume that in our big study, it'll be round about the order, the ballpark of 4 months. Or you may just have to use intuition. From everything I know, I think it will be reasonable that we will probably see a difference of about 4 months. Of course, as your study proceeds and your results start coming in, so you will get confirmation of whether your initial guess was correct or not. And if it turns out to be wildly wrong, well, then you actually need to go back to your statistician and recalculate the sample size you need. If you find the effect size is very much bigger than you had planned for, that's going to be great news. You'll in fact need a much smaller sample. Now with rats, that may not matter, you're doing them anyway. But for example, with a prospective human study, you might suddenly find that you don't have to recruit 200 patients, you only need to recruit 80, because the sample size is much bigger. The effect size is much bigger than you had anticipated. Let's say the drop in blood pressure was not 140 to 135, it was actually 140 to 115. A much bigger effect than you thought you were going to see on your drug trial. If you recalculate your sample size, it will have become very much smaller, which will be good news for you. If, on the other hand, you find you got it the wrong way around, and the effect size, sadly, is much smaller than you had anticipated, then you're going to discover when you recalculate that your sample size is going to have to be very much bigger than you had thought. So those are the approaches to trying to predict the effect size, which you have to do in order to determine sample. So in other words, again, we are predicting the difference, the sample size we'll need in order to hit a Z of 1.96, which equates to P equals 0.05. So this mathematically is the same thing. You have to take a guess at the effect size, difference in means and standard deviations, in order to have a calculation of the sample size you need. As I said, That's actually, those two together are actually your effect size, means and standard deviations. That's your sample size. Right. Okay. Now, the other thing that's incredibly useful, but people are not always aware of, is that we have three parameters here: sample size, effect size, and power. And sample size is not the only question we can ask. Okay. It's the one we all commonly ask the statistician. What sample size do I need to reach this power, 80%, and this effect size? Okay. But you can easily ask it the other way around. What power will I achieve for this sample size and this effect size? In other words, if you come to me and say, I've got 50 patients, I cannot get more. There are only 50 patients with this disease, or maybe I've only got enough money to run the tests on 50 patients. Okay, this is the effect size I'm expecting. You can say, what power will I achieve? And I can calculate that and say, 80% power, relax, your 50 patients are enough. Or I might say 30% power. In other words, you've only got a 30% chance of showing significance if it's there. Are you prepared to stake, your research career on a 30% chance of showing something if it's there? Or you're going to abandon this experiment or go out and try much, much harder to increase your sample size? So we could ask it that way as well. Or you can ask it the third way around. What's the minimum effect size I can detect if I want 80% power and I've only got 50 patients? And I can calculate that and say, well, I think you'll be able to determine a survival difference between the two groups of rats of 4 months. If it's 3 months, you won't be able to show significance. If it's 2 months, you won't be able to show significance. But if it is 4 months, you should be able to show significance. And then you must decide. If you've got a pretty good idea that the difference will be 4 months, you'll say, that's great, I can go ahead. If your suspicion is that the difference is only 1 month or 2 months, then you know in advance that you're not going to be able to show significance. Because you only have sufficient sample to show a minimum, an effect size of 4 months. You won't be able to show a smaller effect size like 1 month or 2 months or 3 months. So in fact, we can ask any of those three quite usefully. Right. I am aware it's late, but we're going to spend just a few minutes doing some practical applications and calculations of this. So let me go to my favorite stats package. Right, MedCalc, okay. Now, like many things, it's actually got a module for sample size. Okay, let's use the example we've used, comparison of two means. So first thing it asks me is what p-value will you accept as significance? 0.05. What power do you want? That happens to be 1 minus the beta error. So if I put beta error 0.2, that is going to be a power of 0.8. Okay. Other packages may ask for the 0.8 directly. This one asks for the 0.2 that it'll subtract from 1 and give me 80% power, 0.8. But now you see, here's the rub. It's asking me for my results before I've even done the study. What do you think the difference in means will be? Well, let's say I think 4 months between my rats. What standard deviation am I expecting? If we say, for argument's sake, 1 month in each group. It's also asking me whether the group sizes are the same. I'm going to say 1 there, which means that sample size of group 1 is the same as sample size of group 2. Now it can calculate the sample size needed. It's got the power and it's got the effect size, difference and standard deviations. And that's great. Tells me I only need 4 rats, 2 in each group is enough to do it. Okay. Let's say, for argument's sake, that we guess the difference is only going to be 1. It's going to be 8 versus 7 months. Now suddenly we need 34 rats, not 4. Okay. So we could not have calculated that if we hadn't taken an initial guess that the difference in means is going to be only 1 month, not 4 months. Let's say, for argument's sake, that we think the standard deviations are going to be wider. In other words, some rats will live from 0 to 8 months with a mean of 4. Others will live from 4 to 12 months with a mean of 8. Do that. And now the sample size has gone up to 128 needed. So that is why the statistician cannot answer your question until you have given that estimate of how big your sample, your effect is going to be. Your best prediction, even though you haven't yet done the sample. And you can now see just how massive the effect of a difference in samples, effect size is in determining how many subjects, how many samples you actually need. Okay, it's a huge effect. Let's use another sort of typical example. Let's say we're measuring differences in blood pressure. So we think the new drug may drop systolic blood pressure by 10. Let's say from 140 to 130. I think the standard deviations are going to be quite wide. Let's call them about 15. Okay, same in each group. And again, we'll have the same sample size. Right. We need a study of 74. We'll be able to do that. Let's say the difference in means actually turns out to be much less. The drug is much less effective than we thought. It's only going to drop it by 5. Now we suddenly need 286 people to have an 80% chance of showing significance. On the other hand, to end off with, let's say we're lucky and the drug is actually much more effective. Okay. It drops systolic blood pressure by 20. Now we're only going to need a sample size of 20. Okay, so that's why it's absolutely impossible just to tell you what sample size you need without you being able to come up with some prediction of what the experiment is going to turn out. You can't just say, if I compare rats, what's the minimum sample size I need? I'm forced to ask you, well, what difference do you think you're going to find? And again, people then look at me like I'm being difficult or that I haven't quite understood them. I mean, I'm asking them to tell me what the result of the experiment is going to be. Unfortunately, there's no way around that. Right. Now, the final few minutes, going to open up another program called G-Power. This is a free thing that you can download off the internet. It comes from some people in a German university that at very high level does all these calculations in all the different directions. Right, you can see it here. I'm going to do a t-test. And I'm going to do the difference between 2 independent means. That's the classic, okay? Difference between 2 groups of rats. Difference between 2 groups of patients in terms of blood pressure. Right. But now it's giving me the choice of what I want to calculate. Compute required sample size, given alpha, that's the 0.05, power, and effect size. So that's the one we normally go off to the statistician with. Make it a two-tailed. Let's say the effect size is moderate, okay, 0.5. Remember that effect size, that's Cohen's D. That includes both the difference and the standard deviations. And as we've said, a standard figure would be a power of 0.8. The sample sizes are the same. Maybe it wants, I put 2 full stops there, my apologies. Right. Okay. Put a light on here. Right. It's told me that I'm going to require a total sample size of 128 to have an 80% chance of showing a significance if there is indeed a difference. If I'm the very cautious type, let's say, no, I'm not prepared to gamble on 80%. I want a 95% chance I'll show it if it's there. I can do that. Trouble is, I now need a sample size of 210 to increase that power. So it went up from 0.8, okay, which is 128, to 210. To increase my power, my chance of showing significance. If, on the other hand, I thought my effect size was smaller, 0.2 is a small one, even at the 80% level, 788 sample size in order to show it. Right, so that's actually quite sobering. But as I said, this program will look at the things the other way around. Compute achieved power given alpha, sample size, and effect size. Let's try that. Okay, right. So you tell me, I think my effect size is 0.2. In other words, I'm expecting a fairly small effect. Okay. This is my sample size. I've managed to recruit 50 in each group. Okay, that's all I had the money for. Tell me, what will my power be? I can calculate it. Your power is 0.167. So the bad news is, at that sample size, you've only got a 17% chance of showing a statistical difference. Okay, so you must decide if that study is worth it. Even if there is a real difference, you're only going to show significance 17% of the time. In other words, if you did the sampling 100 times, you would get significance in 17 of those and negative significance in 83. So you would probably decide that that study is not worth doing, not with that sample size. Okay. If, on the other hand, you predicted that there's actually going to be a very large effect, okay, like 1, the same sample size, I now tell you, got a 99.8% chance of showing significance, 100% power. You'll say, great, I'm so relieved that my 50 and 50 are enough. And then to end off with, let's just look at it the third way round. Compute effect size. So again, you come to me and you say, I want a power of 0.8. I've got a sample size of 50 and 50. What difference would I be able to show? And I'll be able to tell you, you'll be able to show an effect size D of 0.56. In other words, a moderately large difference. So if you're expecting a moderate or large difference, for example, that your rats will live from survival, go from 8 months to 2 months, you'll jump at that and say, yo, I'm sure it's a big size. I've got a very high chance of finding it. If you think your effect size is going to be small, you'll say, I don't think I'm going to be able to show it because my minimum effect size that I'm powered to do is 0.56, and I suspect it's going to be closer to 0.1 or 0.2. Thank you. I'm either going to do a different study or I'm going to have to go out there and recruit a very much larger sample. Okay. So that is more or less that. Where's our share screen? Right. Okay. And I think 25 to 5 will actually stop at that point. So that gives you some idea of what's required to calculate sample size. But as I've said, it is not something that can just be done because you just describe what you want to do. You have to determine the level of power you want, usually 80%, but you have to make some prediction of just how big the effect size is going to be. We've talked about a difference in means, but it could be a difference in proportions. You may, for example, say, I think the mortality in one group will be 50% and in the other group 40%. And if they've got the same standard deviations, that's going to be a much smaller effect size than a mortality of 50% in one group and 10% in the other group, which is going to be a big effect size. And similarly for correlations, R equals 0.5 is going to be a much bigger effect size than I think the correlation I'll pick up will be R equals 0.2, and so on, and so on. Okay, so let's leave it at that.
Good, thank you so much, Richard, for that. I think this video will be watched over and over and over again, just so that we can really get to understand this. I think I'm going to ask if there's one burning question only, because Pumzile has to close this meeting and go home. So only if there's one burning question will we take it, otherwise we're going to close. Okay, nobody's asking any questions. Thanks again, Richard, and thanks again, everybody, for attending. Just a reminder that in June, we're going to be looking at academic writing. We're going to look at general principles of academic writing, how to write a journal article in our disciplines. We're not going to look at how to do it in the qualitative disciplines. It's a completely different approach. And we will be having sessions in evenings where we can all have a writer's lounge and write together. So thank you everybody for attending, and we'll see you next week. Bye-bye then.
Bye.